All right, this is topics 1.13 and 1.14. It's about modeling functions and other applications. So the idea of modeling, also called regression, is a major component of AP Precalculus curriculum and will be revisited throughout the course. These topics will utilize the graphing calculators heavily and often include context. In Unit 1, we're going to work with regression models for polynomial functions, linear, quadratic, cubic, and quartic, which is a fourth power, and for rational functions. So building regression models on the graphing calculator requires two steps. Step 1 is entering the data to be modeled. Step 2 is selecting the regression model. That's all we're going to have to do to find a model for these functions. To do this, you're going to press the Stat button on the TI-84 and select Edit from the menu. So the Stat button, it shows a picture there, but it is right here. It says Stat on it. And you'll choose the first option, which is Edit. You're going to enter the data into the lists, with L1 being your X values and L2 being your Y values. We'll go through this with a problem in just a second. The next step you're going to do is go back to the Stat menu, and you're going to arrow right to the Calc menu. You'll select the desired regression model. You'll see 1 var stats, 2 var stats, med, but we're going to use these other ones: linreg, quadreg, cubic reg, quartreg, linreg, lnreg. You'll notice that there are two linear regression models. That's linreg. AX plus B and A plus BX. They're exactly the same. It just switches where we're going to put the constant versus the slope. AP Stats uses option 8 a lot, the linreg A plus BX, but it does not make a difference. You'll use L1 for your X list, L2 for your Y list. They are in blue above the 1 and 2 buttons if you press second and then 1 or 2. And then for store reg EQ, it's a very good idea to enter Y1. If you press alpha and then trace, you can select Y1. That way we can use the equation and not have to just write it all down. So let's do an example with this. The age in weeks and weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table. A linear regression, A plus BX, can be used to model these data, where Y is the predicted weight of a baby in kilograms that is X weeks old. We're going to write the equation of the linear model for these data. So we're going to start off, and we're going to turn our calculator on. We're going to hit Stat, and then we're going to hit Edit. I have a bunch of things listed in mine, so I'm going to go up to the top of the list, hit Clear, Enter. Go over, Clear, Enter, so both my lists are empty. Now my L1 list is going to be my X values. So I'm just going to enter them in order. I had 4, Enter, 5, Enter, 6, Enter, 8, and 12. Then I go over, and I'm going to enter my Y values, my current weights. So 4.2, 4.4, 4.8, 5.1, and 5.7. All right, now I need to calculate my actual regression model. To do that, I hit Stat again. I go over to Calc, and then I need to choose my linreg that I want. Our problem said A plus BX, so I want to go down to option 8, press Enter. Notice that L1 and L2 are the selected options for X list and Y list. If they weren't, remember we just hit second and then 1, or second and then 2 for L1 or L2. And it's a very good idea to go down to Store Reg EQ and hit Alpha, Trace, choose Y1. You don't need anything for this FREQ list. And then we go down and we say Calculate. What does this mean? Well, it means A, oops, I hit Graph. Now I have to do all that again. There we go. It means my A value is 3.545 and B is 0.185, which means my linear regression model is Y equals A, which is 3.545, plus B, which is 0.185, times X. Using the linear model from part A, we're going to find the predicted weight in kilograms of a baby that is 10 weeks old. And the tip here is that we can quickly find values that are saved in Y1 from the home screen. So the reason we save this as Y1, now I can clear, and I can say alpha, trace, choose Y1, put in parentheses, and I want to plug in 10 weeks, right? This is going to plug 10 into that equation we just came up with. We get 5.395. And that's in kilograms. Now we're going to add in the weight of a sixth baby, that's 5.3 kilograms. And we're going to determine what we think the age of that baby would be. So we're going to say 5.3 is the weight, and I'm going to set that equal to 3.545 plus 0.185x. And I'm going to solve for x. So I'm going to subtract my 3.545. And I get 1.755 equals 0.185x. And then I'm going to divide by 0.185. And I get that x is about 9.486 weeks. So our 5.3 ounce or kilogram baby, we're going to assume is about 9.5 weeks old. Now we're going to talk about residuals. When we use a model to predict values, we expect our model to produce values reasonably close to the actual values. But our models are not expected to result in exact values, generally speaking. The difference between an actual value and the value predicted by a model is called a residual. So to get a residual, you take the actual value minus the predicted value, which in math symbols, we could write y for your actual minus y with a little hat on it for your predicted. So using the model we found in example 1, we're going to find the residual of a baby that is 5 weeks old and interpret the meaning of that in the context of the problem. So the actual value for a baby that's 5 weeks old was 4.4. The predicted value, I grab my calculator and I again say, okay, oops, not what I wanted to do. Alpha trace y1 of 5, 4.47. To get my residual, I need to take the actual value minus the predicted value. So I need 4.4 minus 4.47, which is negative 0.07. So what does that mean? That means that our actual baby weighed 0.07 kilograms less than predicted. Actual 5 week old baby weighed 0.07 kilograms less than predicted by the model. So actual baby was a little less. Using the model we found in example 1, a baby that was 7.5 weeks old had a residual of negative 0.7 kilograms. What was the actual weight of the 7.5 week old baby? Well, if our residual equals actual minus predicted, right? Our residual is negative 0.7. Our actual we don't know, but we can find our predicted for a 7.5 week old baby. Using my calculator, plug it into my function, and I get 4.9325. Now all I have to do is add that 4.9325. And I get the actual weight of that baby was 4.2325 kilograms, approximately. Now we're going to sketch the residual plot for the 5 data points from the table. So in the table, we had a 4-week-old baby, and their residual, well, let's take our actual, which is 4.2, minus our predicted, which I can easily find by taking y1 of 4. I get negative 0.085. So we're going to make this negative 0.05, negative 0.1, negative 0.15, positive 0.05, positive 0.1, positive 0.15. And we'll make this each week. 1, 2, 3, 4 weeks is right here. So negative 0.085 is about here. For 5-week-old, let's do an arrow there instead. I'll do the same thing. The actual 5-week-old baby was 4.4 minus, plug in my value. For 5 weeks old, I get negative 0.07. Huh, it's almost like I already calculated that. Plug it in, plot it, all right. For a 6-week-old baby, do the same exact thing. 4.8 minus, plug in the value 6, I get positive 0.145. Way up there. And then we have an 8-week-old baby. We'll take 5.1 minus the prediction, which will give me 0.075. So 6, 7, 8, there we go. Right in the middle there. And then we have a 12-week-old baby. I'll take 5.7 minus the predicted value, gives me negative 0.065. So if that's 8, 9, 10, 11, sorry, I got to go off my graph a little. About there. There is my residual plot. Oh, you can't even see it. What am I doing? There we go. My 12th one went a little off the page. On the TI-84 calculator, we can also graph the residual plot. To create a residual plot, we must have already entered the data and calculated the regression model. We'll need to press second and then Y equals to open the stat plot menu. This is one of the biggest errors that people end up on their calculators when they're trying to graph, is that they turn on one of these plots. So always make sure you turn your plot back off at the end. So you'll choose plot 1 where it says off. You'll have to turn plot 1 on. So you'll go over to on. Make sure when you're done you turn it back to off, because otherwise your calculator might have some issues. We generally will want the first plot type. It's just a dot graph. Your X list, your Y list. You can choose your mark, you can choose your color. We need the X list to be L1 and the Y list to be resid. So we need to change Y list from L2 to resid. To do that, you'll press second, stat, and select number 7, which is resid. The plot 1 options should then look as shown. And you'll graph the residual plot by pressing graph. And then a quick shortcut, if you press zoom, and then option 9, it says zoom stat, and it'll take you to just what you want to see of the residual plot. All right, the table above provides data for 8 ordered pairs, x, y. Which function type best models the data in the table, linear, quadratic, cubic, or rational? And we're going to talk about this based on the data, characteristics of the data. So when you're asked what type of function best models some data, you want to start by finding the average rates of change. Average rate of change on each interval. So I'm going to add a row to my table. I won't have an average rate of change on the first, but here I can find an average rate of change. It's the difference in my y values, so 10.6 minus 5, over the difference in my x values. So I get that my first average rate of change is 14. Then I do the same thing, 15.4 minus 10.6 over 0.9 minus 0.4. My average rate of change is 9.6. 17.1 minus 15.4 over 1.2 minus 0.9 is 5.67. 18 minus 17.1 or 1.7 minus 1.2 is 1.8. 16.5 minus 18 over 2.2 minus 1.7 is negative 3. 10.2 minus 16.5 over 2.9 minus 2.2 is negative 9. 2.8 minus 10.2 over 3.4 minus 2.9 is negative 14.8. Now if you look at these values are pretty darn close to the same, just opposite sides of the positive and values, or the positives and negatives. So we're going to say that it would be about quadratic. And our reason will be because average rate of change is approximately symmetric. Has to be approximately. So to write the equation of the regression model for the data, we go back into our calculator and we say, okay, stat, edit. We're going to clear out both lists. I'm going to enter my x values, 0, positive 0.4, 0.9, 1.2, 1.7, 2.2, 2.9, 3.4. I'm going to enter my y values, 5, 10.6, 15.4, 17.1, 18, 16.5, 10.2, and 2.8. Be very careful that you actually get all the right numbers in here, because otherwise your model will be incorrect. Now I'm going to hit stat. I'm going to go to calculate. Now I said a quadratic, so I need to go to quad reg. Cubic reg obviously is cubic. Quart reg is quartic, which is a fourth power. So I'll do quad reg. I want L1 and L2. I want to store it as Y1, and I'm going to calculate. So my A value is on the x squared, B is on the x, and C is at the end. For our purposes right now, we are going to round those numbers to the nearest thousandths place. So y equals negative 4.883 x squared plus 15.958 x plus 4.996. That is our approximate model. And we've got one more problem. The table above has data for 7 ordered pairs. We're going to use a logarithmic regression to construct a natural logarithmic function model for f as y as a function of x. We're going to write an expression for f of x in the form f of x equals a plus b ln of x, where a and b are constants. So, back to what we were doing. We're going to hit stat, edit. Clear out the 2 lists I have now. Enter my new data. X values going in. And y values in list 2. All right. Now we're going to calculate the linear or logarithmic regression. So we're going to hit stat, calc. We're going to go to ln reg. ln reg is your natural logarithmic regression. We got list 1, list 2. We'll always store our function just in case and calculate. A is our constant, B is our coefficient on the ln of x. So our function is approximately y equals, we're using f of x equals 2.863. Nope. Let's go 864. Just going to start that over. All right. F of x equals 2.864 plus 1.818 times ln of x. That is our function. The residual plot is shown below. I want to know the coordinates of point R. The point R is right here. Well, this is quite clearly the second dot in my table. So that x value is definitely going to be the 1.6. Now we have to find the residual for 1.6. Well, remember, to get the residual, I take my actual minus my predicted. My actual is 3.3. My predicted will be what I get when I plug 1.6 into the function I just made. So I get negative 0.418. Approximately, because we'll go 3 decimal places. And now, does the residual for the point R indicate that the model F underestimates or overestimates the value of y at this x value? Well, my residual is below the axis, which means that actual minus predicted was negative, which means the predicted was bigger, which means that our model overestimates because a negative residual means that the predicted is greater than the actual.